In this lesson, we're going to introduce the semiconductor transistor, specifically what will be known as the MOSFET transistor, which is a big long acronym that everyone's mostly forgotten, but it stands for metal oxide semiconductor field effect transistor. We oftentimes refer to a MOSFET as just a FET, a field effect transistor, though there are more than one type of FET. But the most popular type these days is the MOSFET, so when you say FET, most people will assume you are referring to a MOSFET. Now before we get into looking at our first and most ideal model for the MOSFET, let's return to our logic gates and consider the question of how to implement an inverter. So a logic inverter. We'd seen previously that we could implement a diode OR gate by doing something like this, where we might have VA and VB, and here was V out or VF, and we could do a diode AND gate where we have diodes pointing the opposite direction, and we would tie these up to, say, 5 volts. So this worked. It didn't have very good static discipline because really it's more like a max or min function. VF here was really equal to the max of VA and VB, and here this was going to be the min. Actually this would be, and we'd put 0 volts as well. So in other words, like if VA and VB were like minus 10 volts, the output voltage would be 0 volts because the diodes would be off, and the resistor would basically tie VF to ground potential. For this AND gate, what we really have is it would be the minimum of VA, VB, and 5 volts. So it's not exactly a true logic AND or OR gate, but we saw some applications where it would actually function. It could serve a purpose of ORing or ANDing. But we have this problem with an inverter that when the input is low, the output needs to be high, and when the input is high, the output needs to be low. Thus an inversion. And there's no real good way to do that without, as we will see, having a transistor. Now let's consider a type of inverter. And we're going to start with something familiar. We will start with the voltage divider, a resistor, a pair of resistors. And here, of course, the output voltage is going to be R1 over R1 plus R2 times 5 volts. And we could rewrite this and say, consider two cases for this resistance R1. And we say, what if R1 was much, much greater than R2? Then this ratio, R1 over R1 plus R2, would be approximately just R1 over R1. So we'd have approximately 5 volts. And if R1 was much, much less than R2, then we would have R1 over R2 approximately, and R2 being much larger would mean that V out was approximately 0 volts. And if we had a device here for our resistor R1 that was a special resistor, it was a variable resistor, and we could somehow control that resistance with a voltage, another voltage that's external to this circuit, such that when we applied some voltage, this resistor would take on a very small value, and when we didn't apply that voltage, or when we applied, say, a 0 volt, that resistor R1 would take on a very large value. If we could do that, then we could implement what would be in effect an inverter. Okay, so how might we come up with a resistor that changes resistances? Well, it turns out that a transistor, a MOSFET transistor, behaves kind of like a variable resistor. MOSFET transistor has a symbol that looks like this. You'll see a couple different versions, so I'll draw a few of them here. This is a very simple one that's really not complete, but sometimes you'll see it. You'll see this symbol, and the one I will typically draw is one that looks like this. Now these all have names to these terminals. D is for drain, G is for gate, S is for source. Gate is the controlling signal, and the current path will be from the drain through the source. And you can think of this analogously as a like a water faucet if you were controlling water. Okay, the gate is like turning the knob, and the two openings for connecting to your pipes would be the drain and the source, and the water, the main water flow would be from drain in through the drain, out through the source, and what controls whether water flows or not is actually the voltage between this controlling pin called the gate and the source. And in our simple model that we will start out with, and we're going to build several versions of a transistor model. Okay, so just like with the diode, remember we treated the ideal diode as being, when it's on, it's 0 volts, and when it has a V forward of 0 volts, when I is positive, current's positive through it, and it has a here I'll just as a reminder here, ideal diode, because we're going to do a similar thing with the MOSFET. Ideal diode, where we'd have an I forward, a V forward, we would say that V forward is equal to 0 when, okay, don't write that here, let's, V forward is equal to 0 when IF is greater than 0, and IF is equal to 0 when VF is less than 0. And so we know, from further study of the diode that, we can model that as a constant voltage drop diode. We can add a resistance in series with it to have a constant slope model, and then we can really recognize that there's a Shockley, this exponential equation that describes the current and voltage relationship, and then finally we acknowledge that a real diode will also have some ohmic resistance, so you have the Shockley equation plus some series resistance, right? And that's what that's a fairly decent basic model for a diode. Well, we're going to do the same thing for the MOSFET. So in this lecture we're going to limit ourselves to this ideal MOSFET model called the S model. Okay, S model is what the textbook uses. S is for switch. So this is similar to the ideal diode, would mean that switch is closed. When the diode was on, the switch was closed. When the diode was off, the switch was opened. Okay, so here is our model. I'm going to redraw the MOSFET. I'll use this symbol this time because I think that's what the book uses, but you'll see me drawing this guy many, many times. and we'll define a current flowing from the drain to the source. I'll call that IDS. There's a couple other things I should mention about the MOSFET, which will simplify its analysis. The current that goes in through the gate is always 0, which sounds kind of strange. But remember, it's the voltage between the gate and the source that controls the transistor. This is convenient because, we haven't looked at any 3-terminal devices up to this point. They've been 2 terminals. And here we have a 3-terminal device. As I say, we've only looked at 2-terminal device. Actually, that's not technically true because you have used some dependent sources, right? So if you have a source that's a current source and its current is dependent on some voltage, you really have a 3 or maybe even 4-terminal device. We just wouldn't usually draw terminals for the controlling signal. And that's really what this transistor is kind of like. We'll eventually see that one of the ways the transistor behaves is actually as a current source, but that's kind of down the way. So right now we're going to look at it just as operating as a switch. And so let me label one more voltage here. The drain to source voltage. So we have 2 voltages and 1 current that we're going to be working with. The current, remember, the current going in the drain is the current going out of the drain, out of the source. So there's no current going in through the gate. So here's the S model. It says that if VGS is less than some voltage, it's a constant, and we're going to call this, the book uses VT. This is extremely confusing because this is the same notation that we used when we talked about the diode and we talked about thermal voltage. Okay, thermal voltage when talking diodes. All right, here this voltage stands for what's known as the threshold voltage. Threshold voltage is one of the parameters of a MOSFET, and although the book will use VT, and that's a standard that is used, I'm going to try to just to use VTH, just to be clear, so you're not confused and thinking that it's the 25 millivolts. So VTH, this is threshold voltage. All right, and typical, it ranges, but these voltages could be anywhere from 1 volt, and in some processes it might be less than 1 volt, but up to perhaps 5 volts. A typical one that we'll use, typical for small, I'll call it for small or signal devices. Yeah, forget that, I don't want to confuse you. So a typical value that we'll use is 2 volts. Okay. So if the gate to source voltage is less than V threshold, then IDS is going to be equal to 0. Okay, it's off. So in other words, we have, here's drain, here's source, and the switch is open. If VGS is greater than the V threshold, then VDS is equal to 0. So we have a short. It's a controlled switch. Now, when it's shorted, it has no resistance, and when it's open, it has infinite resistance. So if we return to this voltage divider, okay, voltage divider inverter. We said we had R2, and we had 5 volts. Now we had R1 before. Well, I'm going to put this MOSFET in here instead. Call this V out, and now we're going to say V in is this voltage between ground and our gate, and this is VGS. So in other words, i.e. VGS is equal to V in. So we would apply voltage at the gate terminal, and the output would be V out. So what do we have? We have two possible circuits here. If V in is less than V threshold, say that's 2 volts, then what we have is a voltage divider with an open switch, right, like infinite resistance. And we have VO would be equal to, well, it's R1 over R1 plus R2, but R1 is infinite. So it's really infinite over infinite times 5 volts, so we get 5 volts. If V in is greater than V threshold, in other words, greater than 2 volts, then we have a short. And that is precisely what we want to have happen for an inverter. So let's draw the transfer characteristic, which means let's plot V in on the horizontal and VO on the vertical. We'll have 5 volts here, and I have to label V threshold here, VTH. I'll say it's 2 volts. So what does our transfer characteristic look like? When the input voltage is less than the threshold voltage, which is this case here, we say that the transistor is off, it's open, and so we get a full 5 volts at the output, right here. And when V in goes above the threshold, we get a short right here, and so VO is 0 volts. Wow, this is really neat. We get an inverting function. And according to our model, when we transition from being high to low, it goes in a nanovolt. I mean, it goes in a femtovolt. It goes into anything that's less than 2 volts is the results in the switch being open. Anything greater than 2 volts results in the switch being shorted, and so we have an ideal inverter. Now you can guess already that a real transistor is not going to be an exact open and an exact short when the transistor, when we apply a gate to source voltage that's just a hair above or below the threshold. So a more sophisticated model will be needed to capture what's going on. But it does, in fact, if you build the circuit in the lab and you were to make this measurement, VO versus input voltage sweep, you would find that it would look very much like this. However, just not an exact vertical line. It would kind of have a finite slope, though steep, but it would very much work as an inverter. So the transistor has added a unique, a fundamental capability that we didn't have anymore. I want to mention 2 more things before ending this initial lesson here. One is to consider a real, this is just a precursor to what we'll be doing later, but I want to highlight one of the salient features of a transistor which makes it so valuable to the electronic industry and everything electronic. Okay, so a real FET would have this type of a curve here. Let me redraw the VO versus VN. So it would be flat here and here, but in the middle it's going to look more like this, okay? And if I were to zoom in right here, you would find that this has a slope that's steep, but not infinite, but it's steep. Okay, this slope, I'll call it M. Okay, we would find that M is greater than 1. In fact, we could say it's not hard to make it much greater than 1. What's the big deal about that? Well, let me draw a little triangle here. Okay. If I change my input voltage by a little bit, then I don't know if I can show that on here. Let's say I change my input voltage by this much, okay? How much did my output voltage change by? By this much, okay? And that's what I'm trying to show right here by making this triangle with the slope of M. What we see is that delta VO is equal to M times delta Vn. Right around that, if we just kind of zoom in, we make a little tiny change in Vn, we'll get a bigger change in VO. And so if delta Vn is equal, say, to 1 millivolt, and let's say M was equal to minus 30. The reason I say minus is obviously the slope here is a negative slope. As we move to the right, it decreases. Then we would have that delta VO would be equal to minus 30 millivolts. Now never mind the sign. The important point is that you put in a 1 millivolt change and you get out 30 millivolts. This is fabulous. This is really remarkable. This is something totally new. And what it is we have, starts with A, MP amplification. Okay, this is revolutionary. We could not do any of the things that we do in electronics if we did not have a transistor device that actually could produce this functionality of amplification, getting a bigger signal out than the signal that you put in. It's not creating power. Remember, there's a 5-volt power supply here, so it's not like we're breaking the laws of physics. We're just talking about the signal, the voltage, or we could say something similar about current. And that's what is needed even for an inverter here. The fact that we want in a small change or range of input voltage changes, we want the output to slew from being high, like 5 volts, down to something low, like 0 volts. Furthermore, we're going to find that the transistor is useful for a whole lot more than just digital inverter. We can use this same circuit to actually implement an analog amplifier, meaning if I have a sine wave that's plus or minus a millivolt, I can produce a sine wave that is plus or minus 30 millivolts. I put a bunch of those together and I can achieve a lot of gain. And so we'll look at that later. That comes later in actually in a chapter or two. So it's later on in our study of MOSFETs. Last thing I want to mention before closing is one augmentation to our model. Okay, not one that will allow us to study the transistor as an amplifier, but one that gets us a little closer to a real transistor model. So let's look at what's called the SR model. What do you think the R is for? Just like our diode, remember we had our Shockley equation. Well, first it was a 0 volt diode, then it was a 0.7 volt diode, and then we said we can add a constant slope, we can add a resistance in series with our voltage, constant voltage diode. So now what we're going to do is we're going to treat the MOSFET as having what's called an RDS channel resistance. Okay, this is going to be drain, this is source. This still is going to be closed whenever VGS is greater than V threshold. Okay, and it's going to be open when VGS is less than V threshold, just like before. The difference is that, the only difference is that when it's on, go back up here, see if I can copy this, save myself some writing. Program's freezing up a little bit. So now what we'll have, oops, come on, doing weird things. Okay, so we have now, when we're shorted, we have a resistor in series instead of a dead short. Okay, and how that changes our inverter that we had here, I'll just draw it in here. If we have an RS model, so I'll say with RS model, when the switch is on, we actually add in an RDS. And so this voltage is not quite zero. It's going to be RDS, it's a voltage divider, right? Plus, this is R2, plus R2 times 5 volts. Now, if RDS is, say, 10 ohms, and R2 is, say, 1,000 ohms, well, then we have 10 over 1,010 times 5 volts. That's roughly, what is that, 50 millivolts? Roughly. Okay, so it's not quite zero. It would be, but it would be down here, like that. Still has a nice inverting function, but this goes back to, remember how we had to define a static discipline that said you're going to put out a voltage that's when logic high will be at least VO high, and when it's low it'll be at least VO low. We're now seeing how a practical logic inverter might not be able to give us exactly 0 volts for a low or exactly 5 volts for high. I mean, we're still doing 5 volts for high, but we're not getting quite to 0 volts for a low. And so we might want to use a static discipline for this type of a logic inverter that says, okay, my guaranteed VO low is going to be, 200 millivolts. I think I can reasonably get under there with this MOSFET. And of course that would depend a lot on, is your MOSFET really at 10 ohms when it's on, or does that vary from MOSFET to MOSFET? If your circuit is sitting at 100 degrees Celsius, maybe the resistance of that MOSFET goes up to something larger. So you end up deciding on a static discipline that kind of accommodates the range of values that you might encounter with the devices that actually fabricate or make up your logic gate, and that way, even over all the environmental changes and over the fact that there's manufacturing variability, you'll still get a logic inverter that can always meet the static discipline. Okay, so in recap, just real quickly, what we've done is we've introduced a new device, the transistor switch, that has allowed us to augment the set of logic functions that we could implement from just diode OR and diode AND circuits to now we can implement inverters. We have talked about looked at the symbol of the MOSFET transistor, defining the gate, the drain, and the source, and then we presented the S model for the switch, which is our kind of ideal transistor model that actually is quite useful in many circuits. We then used that S model to implement an inverter and showed that the transfer characteristic does fit that of an inverting logic function. We looked a little closer at this transition range here and acknowledged that it's going to have some finite slope, but that is in itself a very powerful thing, because we recognize that with the transistor we can have amplification, which will lead to really an electronics revolution in analog circuits. And lastly, we went back to our S model and augmented it by adding a series resistance, RDS, and we looked at how that would affect the transfer characteristic of our logic inverter, and found that it would just simply change what the output voltage was when it was putting out a logic low, from something exactly 0 down to up to something greater than 0. I should mention here in closing that although we've only looked at using the transistor for a logic inverting function, we acknowledged initially that the OR and the AND, diode OR and diode AND functions were pretty poor circuits, really, as logic circuits. They're more like a min or a max function. And now what we can do, or I'll leave this up to you to think about or to look it up, we can use transistors, and we'll use transistors to implement OR circuits, OR gates, and AND gates, because after all, we want to have a nice sharp transition, which we can never achieve using just diodes.